Problem statement. The 260 millimeters outer impeller diameter pump represented in the figure below is used to move water in a piping system. The pipeline has the following characteristics: diameter, length, F, sum of K. Determine the actual flow discharge and the pump head when four pumps in series, the pumps in series we have to use the 260 millimeter impeller diameter, are used. The elevation difference between the reservoirs is 275 meters. Okay, so from here, theta 2 minus theta 1 is equal to 275 meters. And the problem is asking us that we have to use the 260 millimeter impeller. So we have to use that pump curve. So the pump curve we should be using is this one. Okay. So again, whenever we have problems of pumps, we have to find the intersection between the pump curve and the system curve. So this is the pump curve, and then this is the system curve. The pump curve is always going down, and the system curve is going up. And this intersection will give me the actual flow discharge and the actual head. Okay, so then I need to find the system curve and the pump curve. So let's start with the system curve or the hydraulics curve. System curve. So the system curve or hydraulics curve is obtained by the formula HP is equal to zeta 2 minus zeta 1 plus FLD plus sum of K times Q square divided by 2 times gravity area square. Okay, so if we plug values, here we will have HP is equal to zeta 2 minus zeta 1, that is 275 meters, plus F is equal to 0.02. The pipe length is 350. The diameter is 0.3 meters, plus sum of K is 4.2 times Q square divided by 2 times gravity is 9.8 and times area square. The area is equal to pi times 0.3 square divided by 4, all of it to the square because it's asking me area square. So if we use the calculators, we are going to get HP is equal to 275 plus 281.1 Q square. Okay, of course here HP is in meters and Q is in cubic meters per second. Okay, um, so this is my system curve. Now I have to find the pump curve. Okay, but I have to find the pump curve for four pumps in series. Four pumps in series using this pump here, right? This. Okay, but here I have the pump curve in the chart, of course, for one pump, right? For one pump. So first, let's obtain the pump curve, the pump curve equation for one single pump. Okay, so let's use here. So now we are going to use, let's find the pump curve, right? Of course, one single pump, right? Because that's what we have in the chart, one single pump. Okay, so to be able to find the pump curve, here we need 3 points. We know that this curve is a quadratic. It's quadratic. So if the curve is quadratic, we need 3 points to represent that curve. Okay, so the first point to represent this curve typically is the initial point, the when q is equal to 0, and then the end point. And then we have to find one more point somewhere in the middle. And we mentioned before that it's very critical that, oops, let me remove this. So if we use this line here, we have to find a point that more or less um, have or divide this uh, distance more or less in two. So we can choose, example, this point, or we can choose somewhere this point, because that is kind of dividing the the head between the beginning and the end, more or less uh, in two parts, and in that way we are representing the curve properly. Example, you cannot, I mean, I wouldn't recommend to use a point like this point here, because this point pretty much have a head of 90 meters, so you are not, you will not represent the curve properly. So we have to find a point where we represent the difference in heads, right? Uh, so we are going to either use this point, or yeah, probably this point is a good option, because if we use this point, more or less we are representing this. So this is one, and the other one would be this. So it's more or less distributed, and we are representing the curve, uh, you know, properly. Okay, so then we are going to pick those 3 points, and with those 3 points, I'm going to build a table. Okay, so we are going to build here a table. Uh, the table, then we'll have the HP, of course, and the HP is in meters. And then the chart is telling me or is giving me the information in cubic meters per hour. So I have to have the Q in cubic meters per hour. However, in the equations, I have to use Q in cubic meters per second. So I have to also do the conversion to Q cubic meters per second. And this is used for the equations, and this is used for the chart, for the chart. Okay, so the first point will be the initial point. So the initial point, which is here. In this point, of course, the flow is 0 and the head is 90. So that has to be there. Okay, so HP will be 90 and the flow is 0. Of course, the conversion also is going to be 0. The second point will be the ending point. So basically this point here, the end. And that is giving me a head of about 66 meters. And the flow discharge will be about 380 cubic meters per hour. So it's going to be 66, and this is going to be 380. To convert to cubic meters per second, we have to divide by 3,600, because 1 hour is equal to 3,600 seconds. So that will give me a value of 0.1055. Now we need one more point. And as I mentioned before, that point has to be more or less in the middle between the heads. So we can choose, example, this point, right? We can choose this point here, it's 80. So the intersection will be this point. So the head will be 80, and the flow discharge will be more or less closer to 300, 295. Okay, 295. So we can say here, this is 80, and this will be 295. And 295 divided by 3,600 gives me a value of 0.082. Okay, so now we have the 3 points, and with those 3 points, we can build the quadratic equation, which is HP is equal to AQ squared plus BQ plus C. And I am going to find the points A, B, and C. Okay. Not We should note that the Q is in cubic meters per second. Okay. Okay, so we have this. Now, what we are going to do is we are going to use the 3 points and we are going to plug those 3 points in this equation here to be able to find the coefficients A, B, and C. Okay, so let's start with the first point. So for the first point, which is this one, the first point tells me that HP is 90 meters is equal to A Q in cubic meters per second, so 0 to the square plus B times 0 plus C. Of course, this is 0, 0, therefore C will be equal to 90 meters, right? C will be 90. Okay, so we know C now. Now we can use the second point. So the second point. For the second point, we have 66 is equal to A Q squared. Q is 0.1055 squared plus B times Q, and Q is 0.1055 plus C. But I already know C, and C was 90, right? C 90. And then finally, for the third point, and the third point is 80 is equal to A, and the flow is 0.082 squared plus B times 0.082 plus 90. So here I have two unknowns and two equations, and I think this should be straightforward to solve. From here, the value of A is going to be minus 4,488.3, and the value of B is equal to 246. Therefore, the pump curve will be HP, so this is the pump curve, of course, for one single pump, is equal to AQ squared plus BQ plus 6. So this is going to be minus 4,488.3 Q squared plus BQ, 246Q, plus C, and C is 90. Okay, so this is the pump curve for one single pump. One single pump. The problem is, what is the flow discharge on the head for four pumps in series, right? So four pumps in series. So now we say four pumps in series. We know that the HP, the pump head of the system curve, has to be equal to the pump curve, um, right? The HP of the system curve has to be to the HP of the pump curve, right? It has to be to the HP of the pump curve, and that the intersection will give me the flow and the head. Okay, so we can say, okay, my um, hydraulics curve is equal to 275 plus 281.1 Q squared, and that is always fixed. This doesn't matter how many pumps I have, the system curve does not change. And that will be equal to the HP of the pump curve. Now we have four pumps in series, so we have to multiply by 4. 4 times the pump curve, this is for a single pump, so it's minus 4,488.3 Q squared plus 246 Q plus 90. So from this, we are going to get two solutions because we have a quadratic equation. So Q1 is equal to 0.100 cubic meters per second, and the value of Q sub 2 is equal to minus 0.046 cubic meters per second. Of course, the flow has to be positive, so this is not possible. So the flow will be 0.1 cubic meters per second, right? So if you want to convert this to cubic meters per hour, we have to multiply by 3,600, and that will be 360 cubic meters per hour. That will be the flow. So now, if we want to get the head, then we can plug the values in the curve, in the system curve, or in the pump curve, right? So, okay, so to get HP is the formula is 275 plus 281, 281.1 times Q squared, but Q is equal to 0.1, right? So Q is going to be 0.1 to the square, and that will give me a value of 277.81 meters. Therefore, the head is 277.8 meters, and the flow discharge is 0.1 cubic meters per second or 360 cubic meters per hour. Those will be the answers.